Hi everyone, Dr. J here, and in this video we're going to talk a little bit more about reference frames, geodetic datums, and coordinate systems. So the idea here is that you see on the screen there, a geodetic datum is an abstract coordinate system with a reference surface. These geodetic datums and reference frames function as it's a coordinate system that we can use to relate things to where they are, to each other. And of course, probably many of you have heard this saying, location, location, location. Location is everything. If you want to buy a house, the location is very important. If you want to build a building, you have to determine where the property boundaries are and where you can build. So you have to know where things are. Those of you who like to play video games, Minecraft is a classic example where everything is in a particular location. Now, it's interesting that before 50 years ago, or maybe 100 years ago, it could be really quite complicated and difficult to determine your precise location, especially if you didn't have a landmark which had been surveyed astronomically. And this is actually one of the main ways that people would determine locations back in the day, and even still today, people do this, is to use the position of the stars, the sun and the moon sometimes, depending on what you're doing, to determine your position. And really the position of the stars, using the stars to determine your precise location is still really a very accurate way to tell where you are. But this is quite complicated, as you can imagine, pretty labor intensive, hard to do. And you can see just in this example map here on the right, 1719 Hermann Moll's world map, and that's superimposed on a modern map, or excuse me, the modern map is superimposed on the old map. And you can see that there's been some change in the location of coastlines, and of course, that's not because those coastline locations have actually changed. It's because they didn't know exactly where they were. They weren't able to determine those locations as precisely as they needed to. And you can actually see that longitude is the more inaccurate measurement here. And longitude in particular was something that was very hard to measure in the past. Longitude is based off of the prime meridian. So one particular coordinate system that we use is the latitude-longitude system. We use the surface of the Earth, or maybe I should say mean sea level of the Earth, as our reference surface, and then latitude and longitude to tell where we are on that surface. Most of the world's navigational maps use Greenwich, England as their prime meridian, and the US did as well. And so an international delegation voted to make it official in 1884. At that point in time, most of the European countries, the US, were using this Greenwich meridian as the prime meridian, and so now we ended up with that. But what does this have to do with the datum? So the whole idea here is that we're in 3D space. We exist in a three-dimensional world, and so in order to tell where we are, we sort of need at least three numbers, and those numbers can be x, y, and z. But if we have that, we have to define what that is relative to. So we need an origin. You need an origin, and you have to define these axes, and you have to define a unit of distance to measure along those axes. All of those things together gives you a coordinate system. Now, there are other types of coordinate system besides just x, y, z. The one that we use often has to do with latitude and longitude. So you can see here on this little globe, there's latitude and longitude marked for a particular point on the surface of this ellipsoid. Now, of course, the Earth is an ellipsoid. It's an oblate spheroid, so it's slightly wider at the equator, slightly squashed at the poles. So this is the kind of information that we need to define a datum. We need to know this surface, where this surface is, how big is the radius of the Earth, for example. Does the radius change with latitude? And in fact, it does. So we have two different fundamental types of datums. Both of them are, if I back up here for a minute, both of them are going to be approximately an ellipsoid, and they're going to be approximately the shape of the Earth, but they're slightly different. So one type of datum is an actual ellipsoid, and you can see examples of ellipsoids here, different types of ellipsoids. And this is an actual ellipsoid. It's a three-dimensional shape, a regular geometrical shape, which you can describe with a function, and that is an approximation to the shape of the Earth. The other type of datum is called a geoid. And the geoid is based on gravity. So we're going to talk a lot about gravity in this class. And we're going to talk about gravity in this video quite a bit, because gravity is really, really important for understanding where you are on Earth. And in fact, it's going to turn out that the surface of the Earth, where we define the surface of the Earth, called the geoid, is based on basically having an equal value of gravity everywhere along that surface. And as you might imagine, if you have mountains or valleys or really dense rock masses like ore deposits, those kinds of things can actually change the value of gravity locally, or change the direction of gravity locally to that area. Around the mountain, there's more mass there that causes a higher gravity value. And so actually the geoid, the shape of the Earth, looks a lot more undulating, a lot more variable than the ellipsoid reference frame or datum looks. So we'll talk about that more. Let's compare these two, geoid, ellipsoid. Ellipsoid is this idealized model of the Earth's surface that assumes the planet is perfectly smooth and homogeneous and has this geometric shape. The geoid is closer to the actual shape of the Earth's surface when all the effects of the irregular distribution of mass inside the planet are taken into account. So it's based on gravity. So however gravity is changing, the geoid is going to follow that. And you can think of the geoid as being kind of a very rough surface. Well, I'll show you some pictures in a little bit what that looks like. And the ellipsoid is kind of like the best fitting geometrical shape, regular geometrical shape to that surface. The geoid is nice because it represents a physically measurable quantity. We can go out and we can measure the acceleration due to gravity, unlike the ellipsoid, which is just a mathematical construct. And the geoid is determined by measuring Earth's gravity field, as I mentioned. The geoid and the ellipsoid are not quite the same. As I said, the geoid can deviate from the ellipsoid by a number of meters, not a huge amount, but a small amount. And this here on the ellipsoid says assumes a perfect sphere. That should actually be assumes a perfect ellipsoid, a perfect ellipsoidal shape, not a sphere. The geoid will change over time if the mass distribution in the Earth changes, whereas the ellipsoid doesn't necessarily change over time. Now, if you've ever used a plumb line or a plumb bob or even a bubble level or a level setup, you're using the geoid to determine your location or what is level, what is straight up and down, right? So the geoid, a plumb line, will hang perpendicular to parallel to the direction of gravity acceleration, perpendicular to the gravity potential. And that plumb line is based on gravity. So it's using the geoid by default. The ellipsoid, though, is very important, is used by GNSS, or the other word for that is GPS. So Global Positioning System or Global Navigation Satellite Systems, GPS and GNSS. We'll talk more about the difference between those later. But GPS uses the ellipsoid. So if you measure your height using GPS, you're getting an ellipsoidal height. But if you're using a plumb line or something like level, you're getting something referenced to the geoid. So pretty important to make sure you understand the difference. The geoid is more accurate than the ellipsoid. It's a more accurate representation of the Earth's surface, but it's more complex and more difficult to work with. And the geoid takes into account the variations in Earth's gravity field, and as I said, caused by the mass distribution inside the planets. So let's talk about gravity. Probably most of you are familiar with gravity, Newton's gravity law. The force of gravity is equal to the gravitational constant, capital G, times two masses. So this is the force between two masses, divided by the square of the distance between mass 1 and mass 2. So the R12 here is the distance between mass 1 and mass 2. And then this 2 represents the square. So we're going to take Newton's gravity law. Now, I've got a note here, which is to sort of remind us just exactly what else is equal to this force. So force, remember from one of Newton's other laws, is also mass times acceleration. And I use the letter A here for acceleration, and then M is mass. I need to pick one of these masses. I'm going to call M1 the mass of, let's say, the Earth. And M2 will be, let's just say, a test mass or my mass. So that will be my mass over here on this side. So now mass times acceleration, M2 times acceleration, is equal to Fg, which is equal to capital G times M1 times M2 divided by R, distance between M1 and M2 squared. And the thing to notice is that M2 cancels out on both sides. And so now you have this acceleration term over here is equal to mass 1 divided by the square of the distance to some point, and the gravitational constant. And this is, of course, the acceleration due to gravity. So little g, I'll just change my letter here, little g, or the acceleration due to gravity, is equal to capital G times M1, mass of the Earth, divided by the square of the distance from the center of the Earth. So this is our gravitational acceleration. Now, gravity is also, you can think about it as a force, but you can also, we say the word gravity, we mean it sometimes as a potential, and is given by just negative of gravitational constant times the mass over a distance. And the gravity field, this is our little g now, this is mass over distance squared. Now, the gravity field is related to the gravity potential. It's the negative gradient of the potential. So think about it as the negative derivative of the potential. It's a gradient because it's in three-dimensional space. And this is just simply the magnitude of the gravity acceleration. So if we were to plug in numbers for the Earth, where we set the radius here, or the distance to be the radius of the Earth, we set the mass to be the mass of the Earth, we would get a value for little g, which is about 9.8 meters per second squared. So what does this look like? This is an image here of the geoid. It's one representation of the geoid. The geoid is an equipotential surface where the gravity potential is equal to a constant. So remember I said we'll think about gravity, a particular value of gravity, as sort of defining the surface of the Earth. So the geoid is one particular equipotential surface, and there are, of course, infinitely many others, depending on what value of gravity you pick. You pick a value of gravity, and you find the surface, identify the surface with that value. That would be some equipotential surface. This particular one is the geoid. Now you can see that the geoid undulates quite a bit. There's a lot of variability in the geoid, and you can see these are anomalies in milligals. A milligal is 1,000th of a gal, which is 1 centimeter per second squared of acceleration. So these are very small variations, but they're still there. They're still real. So what do you think is causing these? Obviously, as I already mentioned, mass changes are causing these, but there's sort of big scale and then smaller scale. There are two bigger scale factors in that acceleration. What are the variables that are causing gravity to be different in different areas on the Earth? Gravity is stronger at the poles because at the poles, the distance to the center of the Earth is actually less. So you can see in this diagram here, the Earth is slightly squashed compared to a perfect sphere. There's a little bit of extra distance at the equator between the surface of the Earth and the center of the Earth. And so this leads to a slightly smaller gravity value, gravity acceleration, at the equator versus at the poles. Now you might say, well, there's more mass at the equator than there is at the poles. There's mass here in this extra area. So what about that? Well, if you look at the equation for the gravity force, remember that equation has mass 1 times mass 2 on top, divided by the square of the distance. So that bottom term is squared. Distance is squared, whereas the mass on top is just the mass by itself. So the fact that you have distance squared, it comes into play stronger. And so the effective distance is actually stronger than the effective mass. And so the gravity field is actually weaker at the equator instead of stronger, even though there is more mass. You also have the acceleration of the Earth as it's rotating. So the rotation of the Earth, of course, is maximum at the equator and is 0 at the poles. So when you're at the pole, you're really not, you'd be just turning in place. Whereas at the equator, you're moving along at about 1,000 miles an hour. Right? The Earth has a circumference of about 25,000 miles and has to go around one time every day. So that's about a little bit more than 1,000 miles an hour. And that varies in some smooth functional way as a function of latitude. The functional form is actually well known. For the world geodetic system, this is an ellipsoidal solution. You can see here, lambda is the latitude, and lots of numbers here. You can get very precise measurement of gravity based on your latitude. Now, one thing I will note here is that many different formulas are given online, and some of them are incorrect. All are at best approximations of the true geoid because there's this ellipsoidal approximation. You assume that you're on an ellipsoid. So this is the kind of the starting point, but we need more. And what is causing these more undulations, these higher frequency undulations or shorter wavelength undulations that we can clearly see in this image? By the way, we'll talk about where we get this image in a minute. These variations are also known as the deflection of the vertical, the difference here between the local down direction of the geoid and of the ellipsoid. And they're caused by variations in mass, as we said. So here's a very simple example. Let's say you have an ocean floor with a flat bottom, except for one seamount where you have extra mass. This extra mass results in extra, just imagine, extra mass causes extra attraction to other mass. That leads to a little hump over that mountain. Now, again, this is very small. This picture is exaggerated for effect, but the effect, the actual gravity effect, is going to be very small, but still measurable. You can actually measure the deflection of the surface of the ocean from seamounts underneath the ocean. And this causes a change, a deflected gravity, a change because of this extra mass here. You can imagine the same thing happens when you have less mass. You'll have a little depression as the. You can imagine the same kind of thing happens as you have if you have less mass. Excuse me. So how do we measure this geoid? Well, we do it with satellite measurements plus ground measurements and integrating those together, and then sort of do an iterative process to refine this estimate of the geoid and re-estimate it. The potential is going to be related to the negative of the gravity acceleration times your height. And if you do this, if you were to sort of look back about 20 years ago, or maybe a little bit further, and look at the estimates of the geoid, something like this is what you would see. And this is probably similar to that 3D image that I showed you earlier, where you see some variations. And again, these are in milligals. High spots are over high topography. Low spots tend to be over low topography. There can also be other effects from the deeper part of the Earth, which can cause low and high gravity. So you see some of that here as well, for example, over here in India. Now, there's been some new satellites that have been launched, and we're going to talk more about these satellites later. But this satellite is called GRACE, the Gravity Recovery and Climate Experiment, and GRACE Follow-On. These two satellites work in the following way. So both of them are traveling together, and the distance between them is very precisely measured. As it's going towards a mass, the front satellite feels that gravitational pull from that extra mass, and it gets sped up a little bit in comparison to the back satellite, which hasn't gone as far. And so the distance between these satellites increases as it starts to approach the mass. It sort of reaches its maximum as both of the satellites are above the mass. And then as they go away, the front satellite feels less mass first. It feels less pull from that extra mass. And so it slows down, and it slows down. The front satellite will slow down before the back satellite. And so they sort of come back together and keep on traveling. And by taking these measurements, we've been able to make very, very precise estimates of the geoid in comparison to what we had in the past. And this is sort of a new iteration of the geoid over the Earth. You see a lot more detail. I can pop back here for a second. You see highs and lows here. You still see those same areas of highs and lows, but now it's much more detailed, much more well-defined. And this is all coming from these satellite observations. Not only that, but these satellites are able to give us time changes that are happening through time of mass on the surface of the Earth. And so we're actually able to get a time-varying geoid. Now, so we've talked about the geoid. There is a standard geoid, which is used for North America. That's NAVD 88, excuse me. The other kind of coordinate system that I mentioned was an ellipsoid, and we have a global coordinate system based on an ellipsoid, and that's WGS 84. And this is, of course, probably the most widely used reference frame. This is the latitude and longitude system, where we have a Earth gravity model, a world magnetic model, and a coordinate reference system, the CRS, which is this EPSG 4326 for two-dimensional latitudes, longitudes, and it's an ellipsoidal shape approximation for the Earth. So this is WGS 84 is a whole system which works together and is self-consistent. So before I go on, let me just say, if you're using latitudes and longitudes, you're using WGS 84 most likely. If you're using three-dimensional latitudes and longitudes, that means that your heights are going to be based on the ellipsoid, not the geoid. So it's very important when you're using WGS 84 that you make sure you understand what are your heights referenced to. Are they referenced to mean sea level? In which case, you're referencing a gravity model. which is a geoid, geoidal heights, or are they referenced to the ellipsoid? Are they ellipsoidal heights? Or are they some other reference frame like a geocentric or centered Earth fixed, ECEF reference frame? So all of these things exist, and you must be very careful, especially with heights, because heights are usually just said, well, 100 meters. Well, is that 100 meters above the ellipsoid? Is it 100 meters above mean sea level? What are you talking about? You have to define that. So something to be very careful about. Another type of coordinate system that I want to mention is a UTM, and this is really a local coordinate system. So when we're talking about UTM, we're talking about local surveys. You can imagine maybe you're doing a GPS survey just for one particular site, and you just decide, I'm going to set this point right here as the reference, and I'm just going to make measurements, maybe even with a tape measure, to different points in my site. And that local reference point, you really don't know where it's located, but you know where everything else is located in reference to that local origin. So you can use this if it's not necessary to tie multiple surveys together. UTM is a way of sort of generalizing this to a point where you actually know what the origin is, and you can relate things to each other, even if you're working on a local scale. So UTM works by establishing a global grid of local benchmarks or origin points and referencing basically those locations. So you know where your origins are. No matter where you are in the world, there's some local origin, which is not too far away from you, and you can reference all your distances to that. This example on the right is one particular type of UTM system. There are a number of different types. Just make sure when you're using UTM that you know which UTM system that you're using so that everything is self-consistent. And yep, as I said, several types of these UTM systems exist. This is another one. Make sure you know which system that you're using. Now, one final thing I want to mention about reference frames, coordinate systems, datums, all of that stuff, is that this is a new area, a growing area, and the National Geodetic Survey is actually going to be including plate motions. So most of us, I'm sure, have heard of plate tectonics. We know that the tectonic plates are moving around on the surface of the Earth. What you may not know is how much they're moving. So this is just an example for the Western Hemisphere where you can kind of see North America is sort of rotating. In this particular reference frame, it's rotating to the west. California and the little bit of North America, which is on the Pacific plate, is moving to the north and west. And South America is moving to the north. This is all within one particular reference frame, right? So we could pick North America to be the reference frame. In that case, North America would be considered fixed, and other tectonic plates would be moving relative to that. All that this means is that plates are moving, tectonic plates are moving, and we need to account for that when we're doing our geodetic reference frame. Here is the velocities compared to stable North America. So you see California is again moving to the north and west, and North America is pretty much still relative to itself. If we assume North America is fixed, this is what it looks like. So what the NGS is going to be doing is defining reference frames with respect to plate tectonic systems. So not only will we know, okay, at this point in time, this is what our position is, but we'll know as time goes on, how is our position changing relative to other points? And you can imagine in places like California, Alaska, places that are across plate boundaries from each other, those locations, those relative locations are going to be changing through time as these plate tectonic motions continue on. So this is really important, a really important next step for our terrestrial reference frame. Okay, so these geodetic coordinate systems, reference frames, datums, they're critical, absolutely critical that you know what reference frames you're using, what coordinate system that you're using. If you're just using latitude and longitude, it's pretty easy. WGS 84 is the most common, but you need to be very careful about heights, and you need to be very careful if you're switching back and forth between UTMs, latitude and longitudes. Make sure you know what coordinate system you're using at all times. These coordinate systems require an origin point, unit of distance, coordinates in 3 dimensions. On Earth, we often use latitude, longitude, height, but you can use X, Y, Z, or even other local or regional coordinate systems. And you must always, always know and specify your coordinate system when working with geospatial or geodetic data. No matter what you're doing, whether that's mapping, surveying, looking at a bridge, looking at a field, looking at something small or large, whatever the scale is, you need to know and specify, make sure the people who are using your data, using your analysis, know what your coordinate system is and can work with that. All right, so that's it for this, and I'll see you in the next video.